Hello students, in today's lecture we are going to solve NCERT exercise problems on mechanical properties of solids from 8.1 to 8.8. This is disclaimer, learning objectives. By the end of this lecture you will able to solve questions on mechanical properties of solids by applying concepts of stress, strain, Young's modulus and shear modulus using proper explanation. So, index. In today's lecture, we will cover exercise problems on mechanical properties of solids. There are total 16 questions in this exercise, but we are going to cover only 8 questions from 8.1 to 8.8. A steel wire of length 4.7 meter and cross-sectional area 3.0 into 10 raised to the power minus 5 meter square stretches by the same amount as a copper wire of length 3.5 meter and cross-sectional area of 4.0 into 10 raised to the power minus 5 meter square under a given load. What is the ratio of the Young's modulus of steel to that of copper? Let's see the solution. So let's start by listing all the information given in the problem. So first, the length of the steel wire is given as 4.7 meters. Area of cross sectional is 3.0 into 10 raised to the power minus 5 meter square. Length of the copper wire is 3.5 meters. Area of cross section of the copper wire A2 equal to 4.0 into 10 raised to the power minus 5 meter square. Change in length delta L1 is equal to delta L2 is equal to delta L. It means both wires stretches by the same amount. So the change in length delta L is the same for both. Alright. Let force applied in both the cases is F, and for the steel wire the Young's modulus Y1 is given by F divided by area into L1 divided by delta L. Alright. So when we substitute the values in the formula of the Young's modulus, you will get the answer. Now formula for Young's modulus for the steel wire Y1 is equal to F divided by A1 into L1 divided by delta L. So substituting the given values for the steel wire, we have Y1 equal to F into 4.7 divided by 3.0 into 10 raised to the power minus 5 into delta L. Young's modulus of the copper wire. So the approach is same. So Y2 equal to F divided by A2 into L2 divided by delta L. So now again substitute the values for the copper wire. We get Y2 equal to F into 3.5 divided by 4.0 into 10 raised to the power minus 5 into delta L. So now we have two equations, first and second. Alright. So Young's modulus for steel and copper wire respectively are Y1 equal to F into 4.7 divided by 3.0 into 10 raised to the power minus 5 into delta L, and y2 equal to f into 3.5 divided by 4.0 into 10 raised to the power minus 5 into delta L. Alright, so we have a two equation, equation first and equation second. So dividing first by second, we get y1 upon y2 is equal to 4.7 into 4.0 into 10 raised to the power minus 5 divided by 3.0 into 10 raised to the power minus 5 into 3.5. So solving this calculation, you will be get 1.79 ratio 1. This means steel is about 1.79 times stiffer than copper under these conditions. So the ratio of the Young's modulus of steel to that of copper is 1.79 to 1. Figure 8.9 shows the strain stress curve for a given material. What are Young's modulus? In a question ask about the what are the Young's modulus, and B, approximately yield strength for this material. Let's see the solution. So let's begin by solving part A of the question, which asks for Young's modulus. So from the graph, we can see that when the stress is 150 times 10 to the power of 6 newtons per square meter, the corresponding strain is 0.002. The formula for Young's modulus is y equal to stress divided by strain. Here y stands for Young's modulus. Stress is the force per unit area in newtons per square meter, and strain is the change in length divided by original length. So now let's substitute the values from the graph into the formula. We have y equal to 150 into 10 raised to the power 6 divided by 0.002. Alright. So solving for Young's modulus, so we have y equal to 150 into 10 raised to the power 6 divided by 0.002. So when we calculate this, we get y equal to 7.5 into 10 raised to the power 10 Newton per meter square. So we can say Young's modulus for the given material is 7.5 into 10 raised to the power 10 Newton per meter square. Now let's move on to part B of the question. Here question asks about the approximate yield strength of the material. Yield strength is defined as the maximum stress a material can sustain without crossing its elastic limit. So looking at the graph, we can see that yield strength is about 300 times 10 to the power 6 Newton per meter square, or we can say 3 into 10 raised to the power 8 Newton per meter square. Alright. So next one, stress strain graphs for material A and B are shown in figure 8.10. Graphs are drawn to the same scale. We have stress strain graph A and stress strain graph B. A, which of the materials has the greater Young's modulus? B, which of the two is the stronger material? Alright, let's see the solution. So first let's focus on part A of the question. For a given strain, we see that the stress value for material A is higher than for material B. Alright, so Young's modulus is defined as the ratio of stress to strain. So Young's modulus is equal to stress divided by strain. For a given strain, if the stress for a material is more, then Young's modulus is also greater for that material. So also material A has a steeper slope compared to material B. It has a higher Young's modulus. Alright. So Young's modulus for material A is greater than for material B. Amount of stress required for fracturing a material corresponding to its fracture point gives the strength of that material. So fracture point is the extreme point in a stress curve. So this can be observed that material A can withstand more strain than material B. Hence material A is stronger than material B. Read the following two statements below carefully and state with reasons if it is true or false. A. Young's modulus of rubber is greater than that of steel. B. Stretching of a coil is determined by its shear modulus. Let's see the solution. First, let's focus on a statement A. Young's modulus of rubber is greater than that of steel. Right? We will analyze whether this is true or false and then discuss the reasoning behind it. So this statement is actually false. It's important to recognize that even though rubber can stretch a lot, that does not mean it has a higher Young's modulus than steel. Let's see why. So Young's modulus, often represented by the letter Y, measures how stiff a material is. The formula for Young's modulus, Y equal to stress divided by strain. So for the same amount of stress, rubber stretches much more than steel does. That means the strain in rubber is much higher than in steel when you pull or them with the same force. This shows us that rubber is much easier to deform than steel. Since Young's modulus is the ratio of stress to strain and rubber has a much larger strain for the same stress, its Young's modulus is actually much lower than that of steel. So the more a material stretches, the lower its Young's modulus. So steel has a much higher Young's modulus than rubber. This means steel is much stiffer and resists deformation much more than rubber. Alright. Now, statement B says that the stretching of a coil is determined by its shear modulus. So this statement is actually true. Reason: when a coil such as a helical spring is stretched, the primary deformation experienced by the wire material within the coil is a twisting or shearing action, not a change in its length. The shear modulus, which we usually denote as G, tells us how resistant a material is to this kind of twisting or shearing. Since the stretching of a coil involves a change in its shape due to these shearing forces, if you increase the shear modulus, the coil becomes harder to stretch. So shear modulus is the key elastic property that determines how much a coil will stretch under a given force. So when you stretch a coil, the length of the wire itself does not change much. Instead, the shape of the coil changes because the bar twists. That's why the shear modulus is the most important factor in determining how much a coil stretches. Two wires of diameter 0.25 cm, one made of steel and the other made of brass, are loaded as shown in figure 8.11. The unloaded length of steel wire is 1.5 meter and that of brass wire is 1.0 meter. Compute the elongations of the steel and the brass wires. Alright, let's start uh, to solve this question. So let's start by listing all information given in the problem. So diameter of both wires which is 0.25 centimeters. Next, the length of the steel wire which is 1.5 meters. Length of the brass wire 1.0 meter. Alright. Now, first let's determine the radius of each wire. Since the diameter is given as 0.25 centimeters, we divide by 2 to get the radius which is 0.125 centimeters. Remember, the radius is half of the diameter. So next, let's calculate the total force acting on the steel wire. Alright. The steel wire supports both the 4 kilogram and 6 kilogram weights. Look at figure. We have a 4 kilogram, this one, and then 6 kilogram. Alright. So the total mass is 10 kilograms. 6 plus 4, 10 kilograms. Using the formula F equal to mg. Alright, where g is the acceleration due to gravity. So just substitute the value. Total mass 4 plus 6 into g. So 4 plus 6 is equal to 10 into g. So 9.8 is equal to 98 Newton. Alright. Now let's focus on the steel wire first. So we will use the concept of Young's modulus, which measures how stiff a material is. The formula for Young's modulus is y1 equal to f1 divided by a1 divided by delta L1 divided by L1. Alright. So here delta L1 is change in length of the steel wire and A1 is area of cross section of the steel wire, which is equal to pi r1 square. Now Young's modulus for steel which is given as 2.0 into 10 raised to the 11 Pascal. Let's write the formula for elongation, which is delta L1 is equal to F1 into L1 divided by A1 into Y1. Alright. So substitute the values for the steel wire into the formula. The force is here F1 is 98 Newton and R1 is 0.125 centimeter. So put the values. So delta L1 is equal to 98 into 1.5 divided by pi into 0.125 into 10 raised to the power minus 2 whole square into 2 into 10 raised to the power 11. Alright, so solving this you will get delta L1. Focusing on the elongation of the steel wire. So delta L1 is equal to 1.49 into 10 raised to the power minus 4 meter. Total force on the brass wire F2 equal to 6 into 9.8. F2 equal to 58.8 Newton. Alright. Now, Young's modulus for brass Y2 equal to F2 divided by A1 divided by delta L2 divided by L2. Where delta L2 equal to change in length, A2 equal to area of cross section of the brass wire. Now, let's focus on finding the elongation of the brass wire. So the formula delta L2 equal to F2 into L2 divided by A2 into Y2. So substitute the values. Delta L2 equal to 58.8 into 1.0 divided by pi into 0.125 into 10 raised to power minus 2 whole square into 0.91 into 10 raised to power 11. Alright. Now solving for elongation of brass wire. So delta L2 is this one. So solving this, you will get delta L2 equal to 1.3 into 10 raised to power minus 4 meter. Elongation of the steel wire is 1.49 into 10 raised to power minus 4 meter. And elongation of steel brass wire 1.3 into 10 raised to power minus 4 meter. Edge of an aluminium cube is 10 centimeter long. One face of the cube is firmly fixed to a vertical wall. A mass of 100 kilogram is then attached to the opposite face of the cube. The shear modulus of aluminium is 25 gigapascal. What is the vertical deflection of this force? So let's start by listing all the information given in the problem. First, edge of the length of the aluminium cube is 10 centimeters, and mass attached to the cube equal to 100 kg. Shear modulus of aluminium 25 gigapascal, and we know the shear modulus, which is equal to shear stress divided by shear strain, or we can say F by A divided by shear strain, where F is applied force, which is equal to mg equal to 100 into 9.8, which is equal to 980 Newton. A is area of one of the four faces of the cube, which is equal to 0.1 into 0.1. So solving this, you will get 0.01 meter square. Alright. Now recall what is the shear modulus is. The shear modulus often represented by the letter G. So it is shear modulus equal to shear stress divided by shear strain. So G equal to F by A divided by delta L by L. So it will be when we rearrange, it will be FL divided by A into delta L. So delta L is equal to FL divided by AG. So substitute the values and you will get delta L. So it will be 980 into 0.1 divided by 10 raised to the power minus 2 into 25 into 10 raised to the power 9. Alright. Solving for vertical deflection of this face. So delta L is equal to 980 into 0.1 divided by 10 raised to the power minus 2 into 25 into 10 raised to the power 9. So after calculating, we find that the vertical deflection. So del 3.92 into 10 raised to the power minus 7 meter. Vertical deflection of this face of the cube is 3.92 into 10 raised to the power minus 7 meter. Four identical hollow cylindrical columns of mild steel support a big structure of mass 50,000 kg. The inner and outer radii of each column are 30 and 60 cm respectively. Assuming the load distribution to be uniform, calculate the compressional strain of each column. Let's see the solution. Let's start by identifying the information given in the problem. So mass of the big structure m equal to 50,000 kg and inner radius of the column r equal to 30 centimeter. Here we need to convert it 30 centimeter to meter. So just divide by 100, you will be get 0.3 meter. Outer radius of the column r equal to 60 centimeter. Again here we need to convert it in meter. So just divide by 100 and you will be get 0.6 meter. Young's modulus of steel y equal to 2 into 10 raised to 11 Pascal. Alright. Total exerted force F equal to mg. So just put the values 50,000 into 9.8. So now since the load is distributed evenly across 4 columns, we divide the total force by 4 to find the force on each column. So F force column is equal to 50,000 into 9.8 divided by 4 is equal to 122,500 Newton. So we know Young's modulus is stress upon strain. So first recall what strain means. Strain is the ratio of change in length to the original length and it's a measure of deformation. The formula we are using here is strain equal to F by A divided by Y. So we know area equal to pi into r square minus r square. So just put the values, you will be get pi into 0.6 whole square minus 0.3 whole square. So solving this expression, you will be get 122,500 divided by pi into 0.6 square minus 0.3 square into 2 into 10 raised to the 11. Solving this term, you will be get 7.22 into 10 raised to the minus 7. Hence the compressional strain of each column is 7.22 into 10 raised to the minus 7. This means each column shortens by a teeny fraction of its length under the weight of the structure. A piece of copper having a rectangular cross section of 15.2 mm into 19.1 mm is pulled in tension with 44,500 Newton force producing only elastic deformation. Calculate the resulting strain. Let's see. So let's start by listing all information given in the problem. Length of the piece of the copper is 19.1 mm. So here we need to convert it mm to meter. So it will be 19.1 into 10 raised to the minus 3 meter. Breadth of the piece of copper is 15.2 mm. Again here we need to convert it meter. So it will be 15.2 into 10 raised to the minus 3 meter. Area of the copper piece A equal to L into B. So substitute the values 19.1 into 10 raised to the minus 3 into 15.2 into 10 raised to the minus 3. So solving this, you will be get 2.9 into 10 raised to the minus 4 meter square. Then here tension force applied on the piece of copper F equal to 44,500 Newton. This is a significant force and it's important to note that the deformation is only elastic, meaning the copper will return to its original shape once the force is removed. So, modulus of elasticity of copper y equal to 1.1 into 10 raised to 11 Newton per meter square. And elasticity, we know stress y equal to stress upon strain. So, F by A divided by strain. So let's focus on what we are solving for, the strain. Strain is the measure of deformation. Strain equal to F divided by A into Y. So substitute the values into the formula. So 44,500 divided by 2.9 into 10 raised to the minus 4 into 1.1 into 10 raised to the 11. So solving this, you will be get 1.393 into 10 raised to the power minus 3. Thank you for your attention. I hope this lesson was helpful. Thank you.